smart circular bridge in Almere is a biocomposite bridge made out of flex fibers and bioresin. It is also equipped with an elaborate structural health monitoring system. The data from this system is being evaluated by Maximillian Weil from the University of Brussels, who is joining me here today. Hello, Maximilian.
Hi, Alexander, and thank you for taking your time today to meet with me to talk about the structural health monitoring system of the smart circular bridge. So today I'll go over some different points of this SHM system. So first I'll give an introduction about the smart circular bridge and the sensors that are placed on this bridge in Almere. After this, I'll detail the different monitoring systems that we have. So first, the environmental monitoring. How are we looking at the environment around the bridge? Secondly, we'll go over the vibration monitoring. So how do we measure these vibrations and how do we translate these into natural frequencies and what's important in these natural frequencies? After this, I'll go over to the strain monitoring. So how do we compensate for the temperature effects of this bridge? And how do we detect the different events and then analyze the impact that they have on the bridge? And then finally, I'll draw a conclusion and give the few key takeaways for everybody to keep in mind from this presentation.
This bridge is called a smart circular bridge. Why is it smart and why is it circular?
So, of course, as we said, the name says it all. It's a smart circular bridge. So, of course, it's a bridge. We have pedestrians and cyclists that need to cross those bridges. It's circular because it's the world's first 100% natural flex fiber bridge with reinforcement bioresin. And this material, so this complex material, promises to be fully recyclable. And then today we're going to be focusing on the smart part of the smart circular bridge. So it's smart because it's equipped with an elaborate sensor system that's monitoring the bridge continuously, which is actually a requirement when using novel materials in the European Union. And we also use some techniques to evaluate the sensor output and give early warnings about this bridge. So shortly about the smart circular bridge installed in Almere. So as I already said, the novel material is flex fiber and it's reinforced with bioresin. So the structure itself is 15 meters long in Almere, and pedestrians and cyclists have already been crossing it since the month of April. So the construction was done at Fibercore in Rotterdam, and then it was placed in Almere, the Netherlands, as we see in the top right figure of this slide. And after it was placed, the handrails were added, and in the end, you have the results in the bottom right figure. All the data that has been gathered since the bridge is placed is available on a public dashboard at the following link or by scanning the QR codes. Don't worry, if you miss it now, it'll come back at the end of this presentation. So a short motivation for doing structural health monitoring on a structure like the smart circular bridge. So first of all, we want to guarantee the safety of the bridge. So we need to validate the designs to ensure they're according to the norms of Europe or the Euro norms. We're looking at service limit states and ultimate limit states to guarantee, of course, that the bridge isn't seeing too much strain or too much vibrations. And additionally, we do some anomaly detection. So we try and see if something new or something anomalous is happening on the bridge, a behavior that we didn't expect from the bridge. The second point is that we want to understand the loading of the bridge. So this is done through an event detection and event analysis. I will show an example of this later in the presentation. And then finally, we do, again, anomaly detection just based on single events. So let's say if you have a car passing over the bridge, which isn't the goal, then this could be an event anomaly. And then finally, we want to gain new insights in the novel materials that is used for this bridge. So, for example, we're looking at the temperature effects, such as the thermal expansion coefficients and the temperature compensation of strain sensors, which is an additional challenge with this new material. We're also doing a creep analysis on the bridge to see how it evolves over time. And so in the end, the goal is to accelerate the introduction of this new material in the construction industry with the goal of making it more sustainable. So finally, now the important part, the smart circular bridge. So the smart part, of course, is referring to the sensors. And in this, we have three types of sensing. So we have the environmental monitoring. This measures different environmental variables around the bridge, such as the relative humidity, the wind speed, wind direction, and air temperature. Next, we have the strain monitoring. So very interestingly, during the construction of this bridge, we were able to embed fiber Bragg grating sensors inside the bridge. So 82 strain sensors and 8 temperature sensors were embedded inside the bridge in order to monitor what's happening inside this bridge. And then finally, we had dynamic monitoring. So we placed 3 accelerometers along the surface of the bridge to measure vibrations in 3 directions. So in the vertical, the longitudinal, and the transversal direction.
And I also understand that you are measuring the environment around the bridge. How do you do that?
So as I said, indeed, one of the 3 main monitorings is the environmental monitoring. So we have a weather station that's placed next to the bridge. And this is measuring the wind speed and wind direction, which results in a wind rose as shown on the left in this slide. And then for the other 3 values that we're measuring, we can see distributions and how they evolve over time. So we have the air humidity, air temperature, and the air pressure. So we need to measure all these quantities in order to see if they have an effect on the bridge. And then we want to normalize for this effect, as we want to see when something happens that isn't due to change in environments, but due to a change in the structure.
During the opening day of the Smart Circular Bridge in Almere, we jumped on the bridge and we could feel the bridge vibrating. How do you measure this vibration and what is so important about it?
So it's very important for these kind of structures to measure the vibrations. First of all, to ensure that the bridge is comfortable. So you don't want to be walking over a bridge where you feel a sort of vibration that resonates inside your body. And then secondly, we're also looking at the frequencies. But for this first case, let's look at the inauguration day. We were 20 people in the middle of the bridge, all jumping together on this bridge. So this is a very extreme event. You're not supposed to see that very often on a pedestrian bridge. But even with this extreme loading, we only had a vibration that's 10 times lower than the allowed maximal according to the Euro norms. So this means that the bridge is highly damped and won't be uncomfortable to pass over.
Maximilian, I can see you're holding a hammer in this picture. Why is that?
Well, this is because we conducted a very specific test on the Smart Circular Bridge of Almere. So we did a roving hammer test to conduct an experimental modal analysis. So this was done at Fiber Core in Rotterdam. And this is done so we can extract different modal parameters of the bridge. So in order to do this, you need to excite the bridge at very specific locations as shown on the grid in the bottom right of this slide. So every green point is somewhere where we hit the bridge with the hammer 3 times. And then we need to measure the vibrations that this excitation has generated in the bridge. And then we can translate this in modal frequencies, damping, and mode shapes. But very interestingly is that we need a hammer that also measures the force that was applied on the bridge. So it's not just any hammer, it's a special hammer that can measure the force. And so once we did this, we could actually look at the modal parameters of this bridge. So we had the frequencies, the damping, and the mode shapes, both in the vertical and the lateral direction. And as we see with the 2 graphs on the right, the identified frequencies shown with the black lines are well outside of the ranges that are defined by the Euro norm. So we have a vertical critical range and the lateral critical range. Additionally, we can also see how the mode shape is identified in the bottom left. So we shown the first vertical mode shape. And so this is a typical shape for this kind of structure.
So after you've hit the bridge with a hammer, how do you monitor the frequency once the bridge is installed?
Well, of course, I'm not standing next to this bridge and hitting it with a hammer continuously. This would be a bit of an overkill. So we're actually using the natural excitation of the bridge in order to monitor the frequencies. So when people walk over the bridge, or when the wind is blowing on the bridge will vibrate. And if these vibrations are high enough, then we can extract the modal frequencies. So we do this for the long term, so continuously. And then we look if there are significant shifts in the modal frequencies. And so here we can see in this slide the long-term monitoring of the frequencies in the vertical range. And we can see that the frequencies located at 6 and at 7 Hertz, they stay outside of the critical range of the Euro norms. But however, there is one frequency at 2 Hertz that's inside this range. But don't panic, this isn't a structural frequency. This is just the frequency of the people walking over the bridge. So once we can monitor these frequencies in the long term, there are a few questions that we can ask ourselves. So first of all, we think, are we actually tracking these modal frequencies accurately? Well, when the bridge is loaded, we have no problem. Then the frequencies are really well tracked and we can continuously identify them. But as the bridge was placed in the Floriade Expo at Almere, at night, very few people were crossing over this bridge. And then we had a challenge to measure the frequencies. So we can see a clear distinction between nights with low wind, as shown in the red box, and nights with a high wind, as shown in the green box. So in the red box, we can see that the frequencies aren't tracked as nicely. So the green and blue dots show the tracked frequencies, and a lot of them are missing when we have low wind speeds, while during the high wind speed nights, shown in the green box, we can see continuous and accurate tracking of the frequencies. Aside from this, we're also looking at day and night effects. So we clearly see a different behavior during the day and then during the night. So this is shown in the purple box in the figure. So during the day, we see a steep drop in the frequencies, and then it rises again and comes back up during the night. And during the night, we see a very small, steady increase in the modal frequency. So the question is, what is causing these shifts? So two things change during the day and the nights. First of all, during the day, we have much more loading at the bridge, people passing over the bridge. And secondly, we have a difference in temperature, and the sunlight is hitting our bridge. And so the structure is warming up. After a short analysis, we have concluded that these effects on the modal frequency are mostly driven by the temperature and not by the load.
You've talked about the embedded strain sensors, but we haven't seen them yet. What are these embedded strain sensors used for?
So as it says in the name, these are strain sensors. So these are actually measuring the strain inside the bridge. And a big challenge that we had with these strain sensors was the temperature compensation. Because this material, this flex fiber, it has a very high thermal insulation compared to steel. We have very localized effects of temperature. So we can't just apply one temperature compensation for the whole bridge. And so when we apply a classical strategy, which means using regression of the strain with temperature inputs, we were able to drastically reduce the spreads of the data. So as you see on the figure on the right here, the distributions, we went from a spread of 900 microstrain to a spread of 200 microstrain, which is a really big improvement, but even 200 microstrain, in our case, it's too much to detect the different events. So we looked at another way of doing temperature compensation, and doing this, I found the Sapgol filter. So this is a filter that will remove a polynomial trend in your data. So as we see in the graph here in blue-green, in blue we have the data of a strain sensor on the top of the bridge, and in orange we have the data of a sensor on the bottom of the bridge. Well, using the filter, we can accurately follow the trends without removing the different events, which are shown by very small, steep vertical lines. So if you remove the trends from the data, we get the brown and the purple line, which are the temperature compensated strain data. And from this, we can analyze the different events. I've decided today to talk to you a bit more about one such event, and this is the static load test that was conducted on the Almere Smart Circular Bridge during the month of November. So during this test, 4 cubic meters of water were placed one by one on the surface of the bridge, in the middle of the bridge. And so these were placed using a crane, as shown in the top right figure. And then in the end, we had the 4 tons in the middle of the bridge, as shown in the bottom right picture, and the setup is shown in the bottom left as a drawing. So as said, every block was placed one by one with a 10-minute interval in order to measure the strain for every loading situation. So with 1 cubic meter, 2, 3, and then 4. And then after all 4 were placed on the bridge, we waited half an hour. And then after this, the blocks were removed with 5-minute intervals. And so after looking at the data and using the temperature compensation methods, these strains remain for the bottom center north line, so one of the strain lines in the bottom of the bridge. So interestingly, in these strain lines, we can clearly see the shifts that happen in strain when applying the different cubic meters or tons on top of the bridge, and then the same in reverse when the loads are removed from the bridge. And so after this, we can analyze the impact that it has on the bridge.
We can clearly see that the loads are being placed and removed, but how can we know where the load is located on the bridge?
Well, this is where our very complex and very complete grid of strain sensors helps us. So I did some location plots, so where every sensor on the bridge is represented with a small circle in the figure as shown here. And then the size and the color inside of the small circle represents the strain that is actually measured at this location. So what I did is then I plotted these for the different loading scenarios of this test. So this is the strain that was measured when the first ton was placed. And then after placing the second ton, we can see that the strains are increasing because the small circles are getting bigger and the colors are getting more intense. And so we can clearly see, in this case, that the loading was placed in the middle of the bridge. So if we continue to the third ton place, we can even see an increase in it, especially in the middle of the bridge. And then the fourth ton, which was the maximal loading, sees very big and dark circles, which means maximal strain measured.
Thank you very much, Maximilian, for this in-depth analysis of the structural health monitoring. If you want us to remember some key takeaways, what would they be?
So first of all, I want you to remember that this is a smart circular bridge, so with an accent on the smart. And the goal of this smart part of the bridge is to accelerate the introduction of biocomposite materials in the construction industry. So secondly, don't hesitate to have a look at the data that's available through the dashboard. We also have 3 different types of monitoring. So the environmental monitoring, which is looking at the wind, the humidity, the temperature, and the pressure. And we need this data to look at the effect of the environment on the bridge. Secondly, we have the vibration monitoring. Here we're looking at maximal vibrations to ensure that the bridge is still comfortable to walk over. We're also looking at the natural frequencies through a controlled and a field test. So the control test with the hammer inside, and then the field test, the continuous monitoring outside. And we did a long-term monitoring then of these frequencies outside to ensure that they are outside of the critical range as stated in the Euro norms. And then thirdly, and finally, we have the strain monitoring. So this structure was quite challenging for temperature compensation because of the high thermal insulation. And so we had a new filter-based approach for this. And then finally, we looked at an event analysis for the static load test. So we clearly see that we can see for every different sensor how high the strain is for the different loading cases.
What lessons have we learned from the structural health monitoring system in Almere?
So thanks to the monitoring system in Almere, we've learned a few things about the bridge and the material that's used. So first of all, the material. This material is highly damped, so much more than traditional materials that are used for bridges like steel or concrete. Also, we saw that the temperature effects, actually, it's harder to compensate for them because they're not just based on one constant as you have in steel, but it's more complex. And then finally, using the static load test, I actually observed a stiffening over time of the material. So this was done through one test. So other tests are needed, of course, to confirm this trend. Secondly, we can talk about the design of the bridge. So the bridge was compliant with all the Euro norms that we have tested it on, as well for frequencies and vibrations. So the design is a success. And then finally, we also updated our sensor setup for the next bridge using the lessons learned from this bridge. So there are a few things that we wanted to measure, but didn't always have the best setup to do this. And so in order to see how we've changed it, stay tuned to see this sensor setup for the Ulm and Bergen-op-Zoom bridge.
You've mentioned it before, but I want to ask you again, where can I find this data? Is it accessible even to me?
So for this first bridge in Almere, we've made a public dashboard that everybody can access just through the link that is shown here in orange on this slide. Or you can also get to it by scanning it with your phone using the QR code. So we have both a version for a computer and one for mobile phones. So no worries. And this will enable you to look at many sensor data that's gathered on the bridge for all the monitoring period from starting from April until today.
Thank you very much, Maximilian, for this in-depth analysis of the structural health monitoring system. Thank you for taking your time and have a great day.
Thank you very much for the interview and the interesting questions, and I hope to see you soon again.